Hello everyone, this is Dr. Marrero from Math Topics. Welcome to this calculus class. If you haven't watched the previous videos, I recommend to do it. So we have so far 3 videos about limit, why is the limit so important, limits and asymptote, that's an exploration, and the other was about continuous functions. So I recommend that you watch those videos from the series. What I have today? I have today one theorem in mathematics that is called the squeeze theorem. And it's a squeeze because we are going to have 2 functions that will be compressing around or closing around one point, and we are going to squeeze another function right in between in order to find the limit of that in-between function. This technique saves the life of many students when they're finding limits. We call these theorems the squeeze theorems. So we have a value of x that we want to find the limit of certain function f, and we're going to use 2 other functions that probably they're going to have an upper bound function, let's call it that way, and a lower bound functions, and we're going to squeeze the third function f right there, and we're going to find the limit. This is today's video. The graph of the functions g and h, let's start with this question, are shown in this figure. It is known that f of x is less than or equal h of x and greater than or equal g of x. This is what I was talking about. I was talking about one upper function, one lower function. You can see it right there. And we are going to find the limit of a certain function f that is in between them when the x approaches to 0. I start with this representation to give you an idea what I'm talking about. So let's say that this is the function f is inside right there, in between those 2 functions. If we can guarantee this statement right here in green, okay, we can say that the limit of the function f when x approaches to 0 is exactly the same as the limit of the function h and the function g, because the function h and the function g have the same limit. Let's say that when the x is approaching to 0, when right here, both functions, the limit is 2. So if that happens, we can say that the limit of the function f is also equal to. This is the squeeze theorem. What do you think? Here we have the formal definition of the theorems, the conditions and the conclusion. The conditions, the function, if the function f of x is less than or equal h of x or greater than or equal g of x on some interval containing x equal a, this is the point that we are going to find the limit, and the limit of g of x and the limit of h of x when x approaches to a is the same, k. The conclusion is as follows. The limit of the function f, the function in between, is also equal a as well. How can we use this? We have to identify the bounding functions that meet the 2 conditions. And number 2, make conclusions about the sandwich function or the squeeze theorem. This is the formal definition. Remember, g of x and h of x, familiar functions. This is important. Let's do one question. These theorems usually is very effective when we work with trigonometrical functions. We have this quotient right here, the limit of the function x squared cosine of 1 over x. The argument is 1 over x. We have to find the limit when the x approaches to 0. Situations like this, in which we are going to have some kind of indetermination here, when we go and apply direct substitution, is when we're going to start thinking about the squeeze theorems. So first, I would like to use the representation of cosine of x and cosine of 1 over x. So something like this. Okay, we are going to have the cosine here. The cosine range, or the range of the cosine, is in between 1 and -1. And this is super important, the range. So we have here, I don't know, the limitation of the range of the cosine. So this function here is 1 over x, cosine of 1 over x is in between 1 and -1. This is important. So I can put it right here. No? The cosine of 1 over x, it doesn't matter what the argument is less than or equal 1, greater than or equal -1. And then we have another element here, which is a parabola, it's a quadratic. And I can do one algebra massage here. What is the algebra massage that I recommend here? I can multiply -1 times x squared everywhere, and the inequality is still valid. So I can multiply -1 times x squared. I can multiply by x squared. So -1 times x squared. The cosine of 1 over x times x squared. And 1 times x squared. So right here we have minus x squared. Here we have x squared times cosine of 1 over x, which is the function, and x squared, right? So now we have the beauty of the squeeze theorems represented without hurting our expression. And this is what is mathematics. Mathematics is transformation, is an invitation to make a transformation without breaking the rules of the mathematics. And what I did right here, it was a function analysis talking about the range of the cosine between 1 and -1, and working with inequalities, and that is the powers of inequality, and multiplying by x squared everywhere. The inequality is still valid, is still the same idea. And now we have the conditions, the first condition of the squeeze theorem. We have a function squeezing in between minus x squared and x squared. So we have that x squared cosine of 1x in between an upper and a lower function. If you want to make sure that you're understanding the problem, you can use decimals and you can graph the function. I'm going to show you right now. Look at the upper function, x squared. And look at the lower function right here, minus x squared. So we have x squared and minus x squared, the upper and the lower function. The black curve here and the purple one. And look at the red, which is the squeezed function in between then around the point x equals 0 is the cosine x squared cosine of 1x. This is the representation. This is the visualization of the problem. And when you have an idea what is the visualization of the problem, you can integrate your algebra and your geometry in your solution. Remember, mathematics is about transformations. It's an invitation to transform using rules, but do not break the rules. So right here, you can say the first condition is met, the function is in between, the limit of the lower function here, when the x is approaching to 0 of minus x squared is equal to 0, the limit of the upper function when the x is approaching to 0 of x squared is also 0. So you can say now that the limit of your function x squared cosine of 1 over x when the x is approaching to 0 is also 0 by the squeeze theorem. And this is the problem today. Finding the upper and the lower bound functions. First criteria. Second criteria, find the limit of the upper and the lower function around the same point. It's the same, so the function in the middle, the sandwich function, limit when the x approaches to the same value, a, in this case is x equals 0, is equal the same limit of f of g and h if we use f, g, and h. I hope that you like it, and I hope that you see the integration between the two perspective, the geometrical perspective, the visualization, and you can zoom in your decimals and you can see the range of the function x squared cosine of 1 over x between 1 and negative 1. Okay? If you like the video, don't forget to give us a like and to share this video and help math topics. Thank you. See you in the next